A solenoid has a radius equal to 3.2 centimeters and it has 800 turns per unit length. The current in the solenoid changes uniformly at a rate of 22 amps per second. We'd like to calculate the magnitude of the electric field at a point near the center of the solenoid at 0.7 centimeters from its center. Now, why do we even have electric field in the solenoid? The current in the solenoid is changing, so its magnetic field is changing, and the flux inside the solenoid is changing. If the flux is changing, then there must be an induced EMF in the solenoid. So along the dashed circular loop, there's an induced EMF. If you look at things from the perspective of a charged particle, like an electron, the electron will move along the circular path. That's the induced current. What makes the electron move? Well, there must be an electric field such that the electron can move. As the electron is moving, work done on the electron by the electric field is equal to the charge of the electron times the induced EMF. And because the electron is moving in a circular path, this is a line integral of the force acting on the electron along the circular path. And it's equal to the EMF in the loop times the charge of the electron. And what is the force acting on the electron? That's the electric field times the electron's charge. Here we can see that the charge of the electron cancels in our formula, and the line integral of the electric field along the circular path is equal to the induced EMF. By Faraday's law, the magnitude of the induced EMF is equal to the absolute value of the time rate of change of the magnetic flux within that loop. So let's combine these two equations. And the magnetic flux is equal to the magnitude of the magnetic field B times the area of the loop, pi r squared, r being 0.7 centimeters, times cosine of 0 because the area vector and the magnetic field vector are parallel. In other words, the magnetic field is perpendicular to the area of the loop. Here cosine 0 is equal to 1, and the magnetic field magnitude is equal to the magnetic field due to a solenoid, which is mu 0 times I times N, I being the current and the solenoid, N being the number of turns per unit length in the solenoid. In the next step, let's substitute the formula for B. Here for the current, I used lowercase I because current is changing with time. Also note that the electric field is uniform and parallel to the circular path, so the line integral over dl is simply equal to E times the circumference of the circular path, which is 2 pi r. Pi's cancel. We have r on the left hand side, r squared on the right hand side, so they simplify. Let's isolate the electric field E. The result for the magnitude of the electric field, it's equal to r times mu 0 n divided by 2 times di dt. All are given variables in the problem. Mu 0 is a physical constant, so we know what that is. Note that in this problem, we did not end up using the radius of the solenoid. So the r in this result is the radius of the circular path in the picture, which is basically the distance between the center of the solenoid and the point of interest, the point at which we are calculating the magnitude of the electric field. Numerically, we get 7.7 times 10 to negative fifth volts per meter for the magnitude of the electric field at 0.7 centimeters from the center of the solenoid.